Okay, in this segment, I want to talk in a little bit more detail about non-blocking send-receive operations. In particular, go over a Ghost cell exchange routine that uses non-blocking send-receive and show how this simplifies the programming fairly considerably. And I'll show a little bit about MPI data types as well and communicators and how they further simplify and generalize patterns like the Ghost cell filling routine. So let's first start by looking at the interface for non-blocking send receive and then dive right into the example. So the basic non-blocking send receive pair in MPI looks exactly like the blocking send receive pair, except, well, one, they are called I send and I receive, and they follow the convention of underscore after all capital MPI, first capital letter, everything else lowercase, and they have one additional argument. And this argument is a return value returned as a pass by reference to an MPI request handle. Okay, so upon calling MPI I send or MPI I receive, the function returns immediately, and it returns an opaque handle that allows the program to query the status of a send or receive operation anytime in the future. So the key is that these functions always return immediately. They never block, and you are not free to overwrite the send or the receive buffer until this request handle has been queried and told you that the operation is complete in the sense that you are free to overwrite these buffers, not necessarily that the message has arrived in the same sense as MPI blocking send receive. So it kind of breaks it up into two steps and allows you to do work in between those two steps, and also doesn't force you to align rendezvous send receive pairs for every operation that you want to perform. So let's take a look at how this might look in a Ghost cell exchange code. Okay, so here is a function that I wrote called non-blocking or NB Ghost exchange. And we're going to first look at the general structure of the function, and then we'll take a more detailed look at the arguments because it raises a few other issues. But otherwise, it's just a 2D grid, and you have your left neighbor and right neighbor. And I use the MPI cart shift functions in order to get my up, down, left, and right neighbor. So every processor calls these functions, and it fills up and up, down, and left, right neighbor. I say shift one in the X direction and one in the Y direction. Okay, and it uses periodic boundaries, and these four values are filled out so everybody knows their neighbor in just two simple lines of code. Obviously, you can write it yourself. Okay, but once you get these neighbors, then the basic structure, ignoring the details of the argument for a second, is that everybody is going to call I send and I receive. Okay, so every single processor goes through this sequence of 8 calls. So they're going to send left, send right, send up, and send down all at the same time. Don't have to line things up and checkerboard it or otherwise synchronize the operations. And when you're all done, you have 8 request handles, one representing each send or receive. And I created an array of 8 request handles. And 8 is hard-coded just because it's not going to change. And the array then can be queried element by element. You can do MPI wait all and pass it an array of request handles, or you can just do it one by one. It doesn't make really a difference because you have to wait anyhow in this situation. But one by one, you return when the request is complete, and the send or receive buffer is free to overwrite depending on which particular request you're talking about. But when you're done with everything, then you can guarantee that it's safe to continue and that the data has arrived because the receive buffer is safe to use, and that the data has been sent because the send buffer is safe to use. Okay, so this is quite a simple structure compared to what had to be done before, and it is the way I always do it. There are also higher level functions to do it with blocking send and receive that I can show in a different segment. Okay, but there's some details that I want to mention here now that make this even a little bit easier. So let's talk about those. So the first thing to point out is that I'm using not MPI COM-world, but I'm using a communicator that I name COM2D, which represents this particular topology. In other words, I have a up, down, left, and right neighbor defined for this communicator. And if I want to use if I want to define some other relationship between the processors, say a tree-like structure, I can define a different communicator and I can define neighbors for that communicator based off of whatever the send and receive structure is. So it's a nice way to abstract communication patterns and encapsulate them if you're doing more than just one type of send and receive pattern. Now in this code with Ghost Cell Exchanges, that's all we're really doing. So typically we just use MPI COM world, but you're always free to define your own communicator in order to define particular patterns of communication. Okay, that's a small detail, but something to notice. The more significant issue is this MPI data type called a column. So notice, for example, if you're doing row major ordering, as you've experienced many times, and you want to send a row of data along a ghost cell, actually, if you want to send a column of data along a ghost cell, so the left or the right boundaries, they're not contiguous in memory, so you would have to copy them into a buffer typically and send that buffer. You don't want to send them one by one because there's high latency involved with individual sends. Packing that buffer is not bad, but it's error prone, it's a little uglier. So you can define new MPI types which represent strided patterns of memory. And then you can use that type when you send. So let's sort of look at it from the outside in. Okay, so once I get my topology, I'm going to do left-right sending. And left-right sending is where the memory is not contiguous. So what I'm saying is I want to start at I want to send a left column of my array CO. And so there's a pointer to the beginning of the memory location, but it's not contiguous. So I want to send one instance of type MPI or of type column. So it's MPI data type is type column. So instead of sending n individual or a buffer of n doubles, I'm sending a buffer of one column. So I have to define what a column is. A column is a particular striding through memory. Okay, anyhow, I'm sending it to the left with a generic tag on the communicator com2d, and I get back my request handle. Okay, and similarly, when I receive, I can receive into the right side. So this is sending to the left. So I receive on the right boundary, the right column, one data type of type MPI column. Okay, so we have to see how we define that data type. That way you don't have to see the packing of the buffers. MPI automatically packs the buffer under the hood according to the pattern you describe in MPI column. Okay, so let me just jump ahead and say, notice when I do up and down, I don't have to do that. I give it a pointer to the first memory location of the row that I want to send. Rows are contiguous. So I do n local MPI doubles up, and I do n local MPI doubles down. So this is the easy case where the particular ghost cells are contiguous. And this is the messier case that we've swept into the MPI implementation. So there's a lot more to say about MPI data types, but simple things like this are the most common use of them. So let's just look at the definition of that MPI data type called column. Okay, so the key snippet of code is highlighted right here. And here's where we create the MPI strided data type that describes the column structure. And the key function is this MPI type vector function. This is a little different from what you see with other types of data building libraries. And this allows you to define strided types. So the way this works, and I will upload some notes talking about the details of it, but I think the interface is pretty simple. You want this new type to have NL elements, okay? And you want them to be, let me look really quickly. It's easier to just show the interface and then go back to the code. So what you're doing is creating this new type, which has a certain number of elements in it. Okay, and they're going to be n of them because they're n ghost cells in our example. Each element can be made up of a block of more than one fundamental element or building block. In this case, it's just one. We're just having n blocks of length 1 double. If you had pairs of doubles you wanted to describe, if you had 2 endpoints altogether, this could be n of block length 2. But we just have n doubles we want to describe. So let's say the block length is 1, just 1 double. There are n of them, and they're strided n plus 2 apart, because to get from column 1 ghost cell to, on the left-hand side, same column, row 1 ghost cell on the left-hand side to row 2 ghost cell, you have to traverse n plus 2 doubles. Okay, so we're going to put our stride here as n plus 2. And here's where MPI is now going to be responsible for the packing. Because once you describe that the pattern in memory you want is n doubles spaced n plus 2 apart, and here's where you put that their basic type is a double, then MPI knows when you do a send operation and you give it a pointer to the beginning address that it's going to pack a buffer striding through memory with stride n plus 2 going over n items, each of which is just 1 element. And then you give it a instance of the new type, a reference to the new type, and it returns this new type by reference. So that created a new MPI data type. You give it whatever name you want, and then you have to commit it as a separate step. And once it's committed, it can be used in MPI operations, most typically MPI send and receive operations, in order to have MPI pack the buffers according to the data layout pattern you describe. So I basically said it all, but to see it in code, I create the data type, I call it a column. There are n of them. Each block is just 1 basic element. They're spaced n plus 2 apart, I call it n local. Original type is MPI double, the new type is column type. I commit column, and then column can be used in MPI. So if we go to like MPI isend routine, we see column can be a type. Okay, so when I say starting at this pointer, I want to send 1 column to the left, it goes into the data type descriptor and says a column is n elements spaced n plus 2 apart, starting at that address. So the invisible buffer that MPI packs honors that pattern, and you don't have to do all the messy code. So now we have a very simple send, receive, ghost cell exchange code that is correct. We don't have to worry about buffering, or don't have to worry about deadlock. And really, it can be generalized just a little bit and wrapped up in something you link to in the future and just use anytime you have one of these stencil-based patterns. That's sort of the philosophy of MPI. You don't have to write at this level all the time, so it's not as bad as it might have initially seemed.